Yeah, I mean, I think that's sort of true, but I still think that near the terminus, Malaspina is carrying a lot of shear stress for sure. I I think it still has a lot of I don't know how different it is from a contained system in that case, and
Also,
it's certainly still producing a ton of melt, and that melt is following potential gradients to the ocean.
but wouldn't you always have, um, I mean, to go to stream power, you use discharge, and discharge is like width. I mean, I'm like boiling it down to very simple, right? But it's like a width times area, or like a width depth velocity style thing. And thus, if you're like in a system where you have like a lot of width, you can't build up the same stream power locally.
I think that would be true if all the source for that stream power was coming from upstream, but there's all the source is local, right? The more you spread the glacier out, the more of that ice gets exposed to melting, and the more water you can produce. And so, in some sense, I think that those two mechanisms cancel out. Yeah, you don't have as much concentration of that water into like a single location where you can produce a lot of stream power, but you're also sort of uh, making that region more susceptible to melt and meltwater production, which I suspect sort of cancels out the effect of the lack
I
of
Yeah, I see what you're saying. Like you're less in the case of like a glacial catchment, there's like a lot of your discharge production, if I like take it to like a catchment scale, it's related to like what happens at the really at the margins. And thus if your margin is like really wide and flat like a pancake, you have more melt. Yeah, interesting.
So I had a question for you, actually. This is something that I've been thinking a lot about with Tim. Is Tim Bartholomew is on the call, right?
Mm-hmm.
Um, if you had to guess in your work, what would you suspect that the relative sort of fluxes of uh, sediment due to fluvial transport is compared to the flux of sediment at the terminus due to this basal freeze-on and melt-out mechanism?
um I think I have it like 1 for fluvial and 2 for basal for Greenland. So two, like the so basal seems to win big time in this. And then this is based on Ellen Enderlin's, where she had something like 55% of the ice was calving versus RACMO, surface mass balance is 45% or something like that, or it was like close, like 50-50. And so if I like propagated, like back of the envelope, propagated those numbers through that I have, I would get something like zero point 0.9 gigatons of sediment from fluvial and suspended sediment load upwelling versus 1.9 for basal concentration sediment. But that's super rough, right? And that's why we're interested in finding out whether that's true or not.
I have to say, Irina, that I'm very surprised to hear that. And why that's why I thought actually the fact that you're going out and sampling this basal ice and trying to constrain that is awesome, because I would have assumed the reverse, given that the fluvial systems are putting out water with suspended sediment every day, and the calving just seems less frequent overall. But are we going to be able to assess that on a sort of fjord by fjord basis at some point down the road?
I mean, so what we can assess well, I think, from remote sensing, and I mean, this is not my work, but Tim could pitch in or Alan could pitch in, is these calving rates, right? We know thicknesses, and I mean, you're at NASA, you know, like people, how well people do that at this moment already. I think what we need to get a better grip on is if we know the size distribution of these, we know the calving flux and we know the size distribution of the icebergs, then how much sediment did that contain initially. And so some of that can come potentially from modeling, where we go back to the theory of sediment being picked up and plucked at the base, and some hopefully will come out of these like field measurements that we're just really starting at the beginning here, I think. I mean, that's not true. Like there's papers from the 90s, and John Andrews, who's one of the scientists who was on this, they are sort of the reference that I used for this like really back of the envelope connection. That being said, Joe, like I think one of the reasons why I got this interest in icebergs was because that it surprised me so much that it would be so much more than all this like raging river stuff.
Yeah.
And actually my Danish collaborator was like somebody who worked on rivers as well, and he got like so intrigued by it too, independently of me, that he like, went out last year already and got some samples. So we're both still surprised by the back of the envelope.
Okay, so related to that then, although I'm sure you'd like to, you can't go to every river in Greenland or every fjord system, even the big ones. Can people go out, if they go out and they hack off a chunk of basal ice from an iceberg, is that useful to you? If people see basal ice at a land terminating portion of the margin, are those useful reference points to you? Does it have to be frozen in order for it to be useful to your analysis? Is that an angle that you're considering at all? A sort of effort in that regard?
Yeah, and so the pilot data set that we have has mostly like bergs in the fjord, but then we have a small data set that's at the margin in Kangerlussuaq in like a land terminating one, because then it becomes more accessible. I think some of these tidewater calving fronts have like sort of sidewalls where potentially there's accessibility, but it will all be like helicopter supported or we like often work from like small boats and like fairly like, I don't know, cheap logistics, and then they are not so accessible. So that would take a bigger project, but then you have to have some data to make the case that we're not totally off. So I think we're building on that initial data set.
Cool. Thank you.
Yeah.
Any other questions for Irina or Doug?
Can I ask a dumb question? This is Laurie Padman. Question for Doug. I think you said it, but I didn't understand the rapid retreat after it pushes as far forward as it can. So can you explain for a physical oceanographer why that happens?
Why the rapid retreat occurs? Yeah, sure. So I mean, a glacier on land can advance so far that the amount of snow is then exactly balanced by the amount of melt, and then it stops, right? In this context, we have glaciers that do that with that advance being facilitated by the sediment. So, the sort of moraine allows the other mass loss mechanism, calving, to be suppressed, and so you get the glacier advancing as far as it can. But then, what if we just consider like a simple mass balance, like accumulation has to be equal to calving minus, or accumulation equals ablation plus calving. If you're in this extended condition where ablation already equals accumulation, and then you add calving back to the mix, then something has to change. The mass, the mass balance globally of that glacier has to change, and to do that, it has to reduce the amount of ablation that occurs. And the only way that it can reduce that amount of ablation is by retreating.
Doug, I'll just jump in here. And one aha moment when I was first wrapping my head around your work, and I think this answers the question, or maybe provides more information and answers the question, is so to get to that point where your ablation processes have the calving added back in, you have to lose the glacier sitting on the shoal, and that happens because the shoal is migrating forward faster than the glacier is moving forward. So in your paper, you have this nice panel that points to this void opening between the shoal and the glacier. And so it's that void opening. It's sort of the sediment is preceding that shoal, is marching forward faster than the glacier can keep up with it. And that's what, is that correct? That's sort of what kicks off. Yeah. I don't know if
absolutely.
that's helpful. Also,
sorry, go ahead.
I was just going to say there's no such thing as dumb questions. So continue your explanation.
Yeah, and what Caitlin just described is also the reason that there's not really like any stable state in this sort of system. For most of the time that the glacier is advancing, it's advancing and that sort of shoal is locked to the front. They're advancing at the same rate because the glacier can only advance as fast as the shoal does. But when they reach this sort of extended position where accumulation equals ablation, you know, the glacier can't advance anymore because it's got no additional sources of mass, but the shoal certainly still can, because it's primarily being moved by fluvial transport, allegedly. And so, you know, the glacier is as far as it can go. The moraine keeps going, and then all of a sudden it's sitting there in that deep water, and, you know, then it wants to float. And when it floats, it loses all that basal resistance and everything calves off and it collapses.
And the speed is rapid because there's enough low level, high surface mass loss area that it's going to burn away quickly.
Well, once it floats, it loses its sort of basal traction. It loses all the force that's keeping it from sort of flowing out into the ocean. And when you lose that, it's gonna, you know, it's a viscous fluid. It wants to thin rapidly. So it floats and it thins. And when it thins, it also calves. But when it thins, it also wants to float more because it's, it's thinner. And it's more difficult for it to maintain contact with the bed below it. And so this is a pretty well-known sort of instability mechanism in tidewater glaciers that variously called the tidewater glacier instability or the marine ice sheet instability, where a glacier that retreats onto a reverse bed slope tends to have an unstable sort of runaway thing, where as it retreats into deep water, it floats and flows faster and gets thinner and flows even faster and gets thinner and flows even faster.
So you're saying that the retrograde slope is a critical aspect of this rapid retreat?
Yeah, definitely.
In the glaciers that you're studying?
Yeah, definitely.
Okay.
But moraines, sort of by their definition, produce retrograde slopes.
Right.
Especially if they're pinned to the front like that. You know, it's this sort of accretionary wedge thing that is always retrograde on the glacier side.
And the retreat timescale for once it leaves the moraine and starts heading backwards, how long does it take?
Both according to the model, many models, and empirically, this is 20, 30-year timescale. Like Columbia is probably our closest well-observed analog, Columbia Glacier and Prince William Sound. And it started undergoing a retreat in 1989. So 30 years later, it's maybe somebody can correct this number if I'm wrong, but in 30 years, it's retreated a little bit over 20 kilometers. So kilometer a year of calving, roughly.
Great, thanks.
I have a quick question, if you don't mind, I jump in if we still have a couple minutes. So I'm curious about the shoal or moraine mobility, and if the ice is, as you say, locked to the moraine. I wonder why, or maybe how you've reconciled this or thought about this, why you would have the moraine moving further downstream, so to speak, versus having ice thicken at that position of the moraine. So instead of having the moraine move, then you would just have ice thickening at that location. So how have you maybe thought about that?
why would it be that rather than the ice just the moraine staying stagnant and the glacier getting larger in place? Why does the moraine move downstream? It's a reasonable question, and in this particular case, the only real sort of response to it is empirical. At least, which is probably the most well-documented case where this sort of advance seems to be occurring. We have measurements at multiple times of rates of sediment evacuation by fluvial transport. Mm-hmm. And so if we go and make our models transport sediment at approximately that rate, this is what happens. If the moraine were entirely coarse sediment and couldn't get moved in this particular manner, then what you're describing is certainly what would happen. If you can't move the moraine, then the glacier is going to override it and just keep flowing and eventually form a new calving front downstream from there, which is like a parameter choice in the context of a model. It just so happens that these structures seem, at least in the Alaska environment, to be sufficiently mobile that their transport outpaces the capacity for the glaciers to grow and override them.
Great. Do we have any other comments or questions?
Yeah.
Is there anybody on? Yeah, go for it.
Yeah, the quick question for Irina, if she's there. And I was just kind of wondering how this concept of basal freeze-in and the difference in mass flux might fit with this idea of kind of this ice shelf filter concept, that ice shelves or ice tongues kind of act as sediment filters, and that you don't have a lot of sediment frozen in those places, that you're really at the terminus there, expending and cleaning out a lot of the sediment, and how that concept fits with the observations of what's in the different locations that the glacier might transport sediment.
Was this a question for Doug or for me, Joe? Because
for you, Irina.
Okay. One of the concepts that is sort of the simple ideas of like, if you're in the cold-based part of the ice sheet versus like in the warm-based, and then you have pickup of sediment and you don't have pickup of sediment. If you go back into the literature of like things being picked up, you find that even in places like, the Camp Century core, they found sediment in the base of the core where like that, the ice sheet is something like 1,600 meter thick there. And so I think even in sort of situations where you're relatively, like in the simple model, you wouldn't be picking up much sediment. There still is, I think they found in that core, like in the bottom 15 meters, there was sediment. And it's not at the concentrations that you find it at the margin, but there is to be learned from like looking at sediment in those cores a bit more too. And so, but yes, it's not a reservoir that gets built up over the entire catchment of ice. I think that's what any of the more theoretical models on like plucking and training of sediment show, is that it's active where like the speeds are high, and where sometimes there is a reservoir of sediment already, like so you have to abrade and build it up.
I think it's a fascinating thing to look at. I think it will be it would be just very intriguing, but very difficult to find the right slices where you can really get the right sort of information on the different sort of reservoirs and transport processes.
Yeah, no, I think you're right. And we're, any of what I said has like these enormous error bars, right? And so like one of the things in our sampling strategy was to like immediately take triplicates of every one like little berg that we're sampling, because like the variability seems so large, and we'll see where this goes. But if we don't collect any data, we're not going to get that much further either.
No, exactly. We got to figure this stuff out. So I think it'll be very interesting to find out. That's all I got for now.
Yeah. Irina, I have one maybe final question, but just to be clear, this sort of potential for Greenland to supply sand as a global resource, those calculations and that consideration was made without accounting for this basal component. Is that true?
Yeah.
The basal sediment? Yeah.
Yep. I mean, they're even simpler than that. They're done based on, because we're thinking that the most useful component of sand is bedload transport or bedload transported sand. And I mean, that's not entirely true, but it's not the suspended sediment component that we had been tracking with satellite data. So then it's almost a direct function of melt going up into the future and then sand transport happening simultaneously with that.
Right. Cool. All right. Well, we've gone 18 minutes over the hour according to my clock, but it was well worth it. And just so everybody knows, the next IARPIC gathering we have for the Glaciers and Sea Level team is about calving ice. So straight to the sea, calving Arctic ice sometime in early October. So as we learned today, that's pertinent not just to sort of glacier mass balance processes, but also to where fresh water ends up and how sediment gets dumped into the ocean. So thanks so much for everybody's time and intellectual energy this afternoon. And thanks again to our speakers, Doug and Irina. It was a pleasure to get you both on the line here, and we really appreciate your presentations.
Yeah, thanks for matching us up too. I think that it was fun to sort of see like the more theoretical work that Doug's doing, and then this like mapping with big error bar stuff. So yeah, it was good. Thanks.
Yeah, thank you.
Thank you, everyone.
All right.
Thanks, everyone.
Well,
Bye.
Thanks all.
adios. Till next time.
Thanks, everybody.
Bye-bye.
Bye.